All right. In the previous lecture, we began looking at vector fields on symplectic manifolds. And now we're going to move on to classify or introduce some particular kinds of vector fields, which will be of great utility in trying to generalize the formalism of classical mechanics. So let's start with a definition. So suppose we have some symplectic manifold. We have some even dimensional manifold and some symplectic form omega. Then, well, it's a manifold, and we can talk about vector fields on the manifold. So a vector field X on this manifold, well, if it was just a manifold by itself, there's not a great deal we could introduce various different kinds of vector fields. But when we have extra data of a symplectic form here, then we can ask questions such as, does the flow generated by X preserve the symplectic form? So we're going to give that a special name. So if you take the flow of the symplectic form omega, you pull it back, and that doesn't change, so it's preserved by this flow here. Of course, we have another expression for that quantity there, using the Lie derivative. So such a vector field, this is a special kind of vector field, not every vector field does this. Such a vector field is called a symplectic vector field. Now in the previous lecture we spoke about Hamiltonian vector fields. And we're going to see that Hamiltonian vector fields give examples of symplectic vector fields, but not necessarily vice versa. Here's an example, more in the form of an exercise, to illustrate a large class of manifolds which give us symplectic and Hamiltonian vector fields. So we suppose that M is just a manifold. So we're not going to assume that M is symplectic at this point. M is just an arbitrary manifold. And let X be a vector field on this manifold. Then, well, this is not symplectic in general, M isn't, but the cotangent bundle is. And this example here supplies us with a ready collection of vector fields on symplectic manifolds. And the way it works is we're going to lift, via this lifting procedure that we discussed several lectures ago, this vector field X to a vector field on the cotangent bundle now, which is a symplectic manifold. And how do we do it? Well, we know how to lift maps. So we define this guy to be the vector which generates the flow, which is precisely the lift of the flow coming from x. Now we know that this cotangent bundle is symplectic, and we have this tautological 1 form, which we can use to get the symplectic 2 form. So we can get this symplectic 2 form like that for this example of the cotangent bundle. And the exercise is to show further that this vector field is not only unique and a lift of the flow with respect to x, but also that it's Hamiltonian. And the Hamiltonian is none other than the internal product of the tautological 1 form with respect to this lifted vector field here. So to do this exercise, you need to, well, take d of h, use some identities from the Lie derivative, show that those are like internal products with respect to omega, and apply the other formulas that we've derived. So we have a ready supply now of examples, and we even have a way to construct Hamilton vector fields on these examples. And we also have this generalized notion of a symplectic vector field. So at this moment, it's sort of reasonable to wonder if symplectic vector fields are Hamilton vector fields. Maybe this definition was useless in the sense that we could have multiple, in the sense that whenever you have a symplectic vector field, it's automatically Hamiltonian. So this example here might even make you suspect that's the case. Well, let's see what happens. So let's ask the question, when is a symplectic vector field Hamilton? It's obvious the other way around is clear, because the Lie derivative with respect to a Hamilton vector field is 0 of the symplectic 2 form. But maybe, there's an L here, maybe these two things are the same. Well, what does it mean to be symplectic as a vector field? Well, if you look at this characterization that we have up here, it turns out that x is symplectic if the internal product with respect to x of omega is closed. And you can just confirm that yourself. Let's do the calculation. So let's give this thing a name. Let's call this alpha x. So alpha x is a 1 form, right? We've taken the internal product of a 2 form with respect to a vector field. So we get a 1 form, and closed means that d alpha x is 0. So let's check that that's the case. It's the same as taking d of I of x of omega. And then what you're meant to notice is that this is equal to d I of x plus ixd. And this is trivial, right? Because this is just 0. D of omega is 0. That's the definition of symplectic 2 form. And then you're meant to remember, we have a formula for that says L of x. But then you look up at the definition of symplectic, and that's 0. So indeed, it's closed. Now, what does it mean to be Hamilton? Well, if you think back to the definition of a Hamiltonian vector field, the way it works is you have this function, the Hamiltonian, you take its exterior derivative, so then it's a 1 form, and that 1 form has to be equal to some vector being put inside the symplectic 2 form with the internal product. So x is Hamiltonian if when you take the internal product of x with respect to omega, it's d of h for some h. But here we see the crucial difference between a symplectic vector field and a Hamilton vector field. So this 1 form here is exact. It's an exact 1 form, the one that comes from a Hamilton vector field. And the 1 form alpha x that comes from a symplectic vector field is closed. But the space of closed 1 forms and the space of exact 1 forms aren't necessarily equal spaces. So the question is it turned out to be rather interesting indeed, whether a vector field, a symplectic vector field is Hamilton or not, appears to depend on global structure. Now, we're not going to discuss cohomology in this course, but if you're familiar with de Rham cohomology groups, then it's equivalent to asking if the equivalence class of this 1 form is trivial or not in the de Rham cohomology group. And that the answer to this question depends on the global topology of the manifold that you have, like whether it has got holes in it or not. So that's rather interesting. If we have an arbitrary manifold, whether or not a symplectic vector field is exact, is Hamilton or not, depends on like whether or not there's holes in the manifold far away. So on global topological information. However, another conclusion is that if we have a connected manifold, which is sort of locally trivial, so you can contract this piece to a point, then in fact all symplectic vector fields are Hamilton. That's the flip side of the coin. So I'll write that out. So locally on any symplectic manifold, a symplectic vector field is a Hamilton vector field. There's no difference. But if you want to extend it to a Hamilton vector field over the entire manifold, then you run into obstructions. So locally, on contractible open sets, I won't define contractible, but you can use your intuition to understand what that definition might be. All symplectic vector fields are in fact Hamilton. And this is really a useful piece of information because it allows us to check if a vector field is Hamilton locally. We don't have to look at the whole global manifold on contractible open sets. We just have to check this symplectic condition. But if we want that our vector field is Hamilton on an entire manifold, which is non-trivial, then we have some harder work to do. All right, so, wait. Let me then just summarize what we've learned about symplectic and Hamilton vector fields. So we have a bunch of equivalent statements. So a vector field is symplectic is equivalent to the flow sigma t of our vector field preserves the symplectic 2 form for all t, which is equivalent to the Lie derivative being 0 of the symplectic 2 form, which is equivalent to I x omega is closed. So that's what we've now learned about symplectic vector fields. There's a bunch of equivalent definitions, and we further learned that symplectic vector fields are Hamilton on locally contractible open sets, but not necessarily globally. Now I've been talking for the whole course about how symplectic geometry is a kind of vast generalization of classical mechanics. So if that's a true statement, if I haven't been lying to you, then I better at least show how classical mechanics gives an instance of a Hamilton vector field on a symplectic manifold. Otherwise, I've been building Baroque theories with no relationship to the things they're meant to generalize. That would be a shame, and it would also be very misleading to give something, to define something with the names Hamilton if it didn't itself generalize Hamilton vector fields as you would get in classical mechanics. So that's, you know, I mean, definitions are never wrong in the sense that you can't prove them wrong, but it's unethical to make a definition that doesn't, and name it in a certain way, if it doesn't generalize something that the name suggests it does. Classical mechanics, okay. We know what classical mechanics is. That's one of the prerequisites for this course, that you've met Hamilton's equations, Lagrangians, Euler-Lagrange equations, all this sort of thing. This is assumed knowledge for this course. And now I want to show how indeed classical mechanics can be formulated in the language of symplectic geometry and gives rise to Hamilton vector fields, as you would hope from the name. So let's do some classical mechanics. So consider Euclidean space. This is the configuration space. Well, this is phase space, actually. So for n degrees of freedom, or a particle with n degrees of freedom. I'm going to label the coordinates in our Hamilton fashion. So the first n are the canonical position coordinates, and then we have the conjugate momentum coordinates here. And now the first thing, which looks a bit unfamiliar from classical mechanics, is we're going to turn phase space into a symplectic manifold. We're free to do so. If we want, we can. We know we can, because there is a two-form on this manifold that's closed. Sort of locally and globally, in fact. So we introduce this symplectic two-form here. Now we have a Hamilton function on phase space. Well, what's that in the language that we've got so far? It's just a function on phase space. Now we have the first departure from the usual formulation of classical mechanics. Well, the symplectic two form, you just ignore that it's there, and then it's looking like classical mechanics. But now we have this vector field corresponding to H. What we want to do is understand the flow generated by this vector field and then show that it's equivalent to Hamilton's equations. So the first non-trivial thing that requires a check is that we have a formula for this vector field x of h. You can form d of h, you can take the internal product of x of h into omega and check that you get d of h, and you do so when you have the following formula for this x of h. It all works out in this case. And we're going to check that. So corresponding to this Hamilton function on phase space, there is this vector field here. Should already start to look pretty familiar. You can check it's a vector field. Look, it's expanded in terms of these basis vectors. Okay, let's check, before we move on, that indeed x of h is the corresponding vector field. So what we want is that that equals d of h, just to check that I haven't been misleading you here. And this calculation is kind of nice because you'll see another way of working with internal products that I didn't highlight yet. I mean, we derived this formula, but I didn't emphasize the practical utility of the next formula. So whenever you have an internal product of the wedge product of two things, then remember this anti-Leibniz property of the internal product. The internal product of this wedge product is like the internal product of this thing minus the internal product of that thing wedged against the other partner. A very useful formula because it allows us to do this, much less scary computation than somehow working out the internal product all in one go from the other definitions I gave. And the internal product of a vector field on a one form is just a number. And that is easy to work out. So dqj internal product with xh should just give us dh dpj. So that becomes a number, and we're left with the dpj there, minus internal product on that one form, which is just again evaluating the one form on the vector, and that should give us dh dqj, but there's a minus sign, so we get that. And look, how neat is that? All right, so it's all good. This is indeed the Hamilton vector field corresponding to the function h. But what does this have to do with classical mechanics? So a trajectory in classical mechanics is a solution to Hamilton's equations. dq dt equals Poisson bracket of h with something and vice versa. So if this vector field x has got to do with classical mechanics, the flow of x should give the trajectories of Hamilton's equations. So if we got the definitions right, if we generalized everything correctly, then this vector field here, its integral curves should be exactly the trajectories in phase space generated by Hamilton's equations. Let's see if that's the case. And if they are, then we know we've got the right generalization. So Hamilton's equations in the more mundane form, how do they read? They read that you take the derivative of the canonical position coordinates and you get the derivative of the Hamiltonian with respect to the momenta, the conjugate momenta, and vice versa, right? That's Hamilton's equations, but with a minus sign along the way. But that's exactly the same as this. Equation here. If you just put in x of h, which is written down here. So indeed, we get that this whole infrastructure is a clean generalization of Hamilton's equations in classical mechanics. So far, everything looks like it's a natural generalization. We haven't made any ethically wrong definitions so far. And so we should be very happy about this because we know we're on the right track. When you know you're on the right track when the things you create are good generalizations of things you know already, and it makes the whole presentation cleaner and more economical. So why stop at trying to reproduce Hamilton's equations? Let's go further. Let's start thinking about other aspects of classical mechanics and start trying to generalize them. Now, one thing you know from classical mechanics is that in Hamilton's equations, you can express the right-hand side in terms of these Poisson brackets, which we'll introduce in a second. So what I want to do now is generalize the notion of a Poisson bracket to a symplectic manifold. And this will turn out to be one of the most useful aspects of the symplectic geometric approach. Because it'll allow us to talk about integrable systems on symplectic manifolds. It's like a big application. Pretty amazing one, actually. So the next part of this lecture is going to be all about brackets, both Lie and Poisson. And to get things started, we're going to observe a fact about symplectic vector fields. So if you have two symplectic vector fields, then we had this operation called the Lie bracket, right? That allows us to build from two vector fields a third vector field. And here it is. So there's our third vector field, the bracket of x and y. And the remarkable consequence that you can observe is that if you have two arbitrary symplectic vector fields, not only is the bracket symplectic, it's actually Hamilton. And the Hamiltonian for this guy is just take your symplectic 2 form and put in it x and y. This is definitely a number. It's a 2 form evaluated on 2 vectors, so better give a number. So it could be the Hamiltonian for something. It's a function on the manifold, it's a Hamiltonian. And this is just it's such a pleasure doing this kind of maths, because when you have these very powerful seeming statements and you've got it right, then the proofs become so simple and elegant. And so this is no exception here. This is a really nice proof. So let's assess whether the vector field x comma y, the bracket of x and y, is Hamilton or not. Well, let's put it into our 2 form with the internal product and hope we get d of omega xy out at the end. And we're going to use this nice observation that we had about internal products of brackets. So the internal product of a bracket is Lie x internal y, minus internal y Lie x. So it's an identity we worked out in the previous lecture to do with the internal product. And then we get some rather nice things happening right now. So then we use the fact that Lie derivative is di plus id, a very useful formula that we can just continually use in this course. And then we see some really nice things happening right here. Yeah. So first of all, d of omega is 0. So that's gone. Then we have that I of x on omega. Well, what is I of x on omega? That's this one form alpha x that I called in the previous part of this lecture. Well, since x is symplectic, I of x on omega is closed, so that means the exterior derivative is 0. Similarly, because y was symplectic, the exterior derivative of I of y on omega is also 0. In fact, we're left with one term. Internal x, internal y, but we're going to do the internal product first of y, then of x. So that's the same as doing y and then x like that. Oh. Yeah, I've got a minus sign wrong. She'll fix up like that. And there we are. We're finished with the proof. Now that thing, this Hamiltonian, omega evaluated on the vector fields x and y, is a number, it's a function, right? Omega evaluated on y and x is a function on the manifold. To evaluate this function, you need to have two symplectic vector fields. And you notice that it's anti-symmetric, so that if you exchange y and x, you get minus x and y, omega of x and y. So this function is a function of two vector fields, and we're going to give it a special name in a minute. I'm going to give it a special name in the case that both y and x are Hamilton. Oh yeah, but before we do that, I'm going to introduce the real Lie algebras before we continue. So before we get to this definition, this proposition here shows us that if we have two symplectic vector fields, we can take their bracket and get another one. So it's sort of tempting now to think about the space of all vector fields under this composition operation of bracket here. And that space of all things will be a space of vector fields, a space of symplectic vector fields, but with this additional bilinear structure there. And we're going to isolate that out here in this definition. And notice that the set of all symplectic vector fields with respect to this bracket operation forms this thing called a real Lie algebra. And we'll have a lot to say about these in the last part of this course. So what is a real Lie algebra? Well, it's a vector space. So you know what those are. And there's a bracket operation, a bilinear operation. It takes two elements of the vector space and gives you a third. And this bracket operation satisfies certain identities, namely that it's anti-symmetric. So for any two pair of vectors, you have that, and it obeys the Jacobi identity. So we know these two properties are true for the Lie bracket. We've proved these already. And just thanks to this proposition, we immediately see that the set of all symplectic vector fields forms a real Lie algebra. It's closed under the bracket. But we see something more, right? We see that all the Hamilton vector fields, immediately, if a vector field is Hamilton and that one's Hamilton, this is also Hamilton. So we see that they form a real Lie algebra, and perhaps, depending on the manifold, a smaller one. And we also see that the set of all vector fields themselves form a real Lie algebra. So let's just formalize what I just said. So we have X of M, the set of all vector fields. That is clearly a subset of all symplectic vector fields. So there's an inclusion there. Every symplectic vector field is a vector, but not the other way around. The inclusion goes that way. And then we have a third class of vector fields, namely Hamilton vector fields. And that proposition there, with its three-line proof, has this really powerful consequence. That not only are these three things sets of vector fields, they're real Lie algebras, and not only are they real Lie algebras, this one's contained in this one's contained in this one. Conclusions of real Lie algebras. This is extremely useful because we know in physics that symmetries, continuous symmetries, are generated by Lie algebras. So we know that the set of vector fields here, generating flows on a manifold, contains as a subset of symmetries just those purely symplectic ones. And indeed, when your manifold is non-trivial, there's a further smaller subset comprising the symmetries generated by Hamilton flows. And now, when we restrict our lives to just Hamilton vector fields, we see that it's natural to introduce something that generalizes the Poisson bracket in classical mechanics. So if you think back to the Poisson bracket of normal classical mechanics, it's a operation which takes two functions on phase space and gives you a number. And we have now at hand an operation which would do this. We're going to denote our generalization as the same notation as in classical mechanics. Takes two smooth functions on the manifold and produces a number. And the recipe for this number is take the symplectic 2 form, that's natural and standard and canonical, right, on a symplectic manifold. And what's the most natural thing to stick inside a 2 form? Well, a vector and a vector, that will give a number. But where are we going to get our vectors from? Well, we get them from these functions. So there we have it. That's an idea for how to generalize the Poisson bracket. It's only a good idea if it generalizes the Poisson bracket. So if we apply this to the setting of Hamilton mechanics, does it look the same? Classical mechanics, when we write this out in coordinates? And of course it does, right? This isn't useless formalism here. So if we write this operation out in coordinates, you'll see that you get the standard Poisson bracket that you know from classical mechanics. So there's an exercise to check that in coordinates for the case of classical mechanics in the symplectic form omega, that you indeed get the standard Poisson bracket. So there's some neat little identities now to notice about this definition. Well, firstly, the Poisson bracket is a function, right? Takes two functions, gives you a function. So you can ask questions about that function. Is this function the Hamiltonian for some vector field? And the answer is, well, yes, it is. And you might wonder which vector field. So by assumption, no, this is the definition of the vector field. And when we put it in the internal product like that, this should equal d of something. And that something had better be the Poisson bracket f g there. But we know something about the internal products with respect to commutators, and we're going to use that fact right now. So if we do the internal product with respect to a commutator of this 2 form, we have a formula for that as well. We derived just before. And so if you compare this formula with this formula, you see that x must be the commutator of f and g. or in fact the minus of the commutator of f and g. It also generalizes what you know from classical mechanics. So now we've got another bracket operation. We have the Lie bracket that takes two vector fields and gives you a vector field. And then we have this Poisson bracket, takes two functions and gives you a function. So we might ask, what are the properties of this bracket operation? Do any of them that we know from classical mechanics remain? And if so, what's the space of all functions closed under this bracket? We'll answer both of these questions. So let's look at some properties. Well, firstly, we know that the Poisson bracket is antisymmetric. Just look at the right-hand side of its definition. So you get a minus sign when you exchange the arguments. Good. It's antisymmetric, so it looks like a Lie bracket a bit, doesn't it? And furthermore, the resemblance to the Lie bracket is much stronger when we notice, that the Poisson bracket also obeys the Jacobi identity. I've been using different notations for the same thing here. Space of all functions on smooth functions on a manifold is C infinity M as well. And so the proof, that's an exercise. I hope not a particularly difficult one when you look at this equation there. So we have a real vector space of all smooth functions on the manifold. We have a Lie bracket, so we got a Lie algebra, but we have more because the space of smooth functions has additional structure that you don't have in the standard real Lie algebra case. Namely, you can multiply two smooth functions and get a third one. So there's a different notion of product. And we're going to capture all of this structure in a following definition. give it a name. It's called a Poisson bracket. It's called a Poisson algebra, and you only get to call it a Poisson algebra, the settable smooth functions, if you have this antisymmetric bracket that obeys the Jacobi identity, and that this bracket respects products of functions pointwise. And that would be the case if it obeys this Leibniz property here. So you can check that this definition that we introduced here of the Poisson bracket does give the space of all smooth functions the structure of a Poisson algebra. So there's a small exercise. So what we get is we get a ready supply of Poisson algebras from symplectic manifolds. Where do you get our Poisson algebras from? Well, you take as P the commutative associative algebra given by smooth functions on the manifold, and as the Poisson bracket. And furthermore, by taking a function and associating with it its corresponding Hamilton vector field, by taking the Hamiltonian, via that map there, and by taking the Poisson bracket and replacing it with the Lie bracket of the corresponding vector fields, that's a Lie algebra anti-homomorphism. So we get a representation of this Poisson algebra via vector fields on a manifold. So we have a little bit of time. I'll mention now something about quantization. So you can think of symplectic manifold as phase space, the set of all configurations of your classical system. You can think of the Poisson of a Poisson algebra as the space of all observables on your classical system. And you know that, of course, there's this thing, however, called quantum mechanics. And in quantum mechanics, you want to associate, or you define your quantum systems also via observables and states. And I mean, it was particularly more relevant in the early development of quantum mechanics, and maybe less so now. We didn't really have a good way to associate quantum systems to classical systems. So let's just crystallize this. So in classical mechanics now, if you're willing to accept that symplectic geometry is a generalization of classical mechanics, you have your space of states, that's phase space. And that corresponds in classical mechanics to just a symplectic manifold. Points in a symplectic manifold are points in phase space, are states of your system. You fully specify the state of the system once you've specified a point in this manifold here. And in quantum mechanics, well, we also have a space of states. Now, what I should say, be a bit careful here, is that these are pure states. Because you can have mixed states also in classical mechanics, and also in quantum mechanics, of course. Right? But the space of pure states in quantum mechanics is a Hilbert space H. In classical mechanics, the space of observables is the Poisson algebra P of smooth functions on the symplectic manifold. So an observable is some function of the state. Easy, right? If I know the state of my system, some point in a manifold, and I want to know the value of an observable, well, the observable is a function. It associates a number to the state, so it has to be a smooth function. And we furthermore know from all of this discussion that this set of smooth functions forms a Poisson algebra, so it's got lots of extra structure there. Now in quantum mechanics, the space of observables is understood to be the bounded operators on Hilbert space. If you're doing things a little bit more carefully and operationally, on the right-hand side, we don't distinguish. In the right-hand side, we just speak of the space of all states in quantum mechanics as being density operators. And we don't usually talk about observables in operational definitions of quantum mechanics. We prefer to speak of POVMs or measurements, space of measurements, which are yes, no, or projections. But I'll be slightly not so careful and talk about the spaces of observables in quantum mechanics and just say it's just B of H. So you look at this, and if you're looking at it through the lens of classical mechanics, thinking that the quantum world is somehow an extension of the classical world, and what we want to do is find out the right way to associate a quantum system to a classical system, then it's very tempting to say that there is some kind of magical map called quantization, which associates to every symplectic manifold, say, a Hilbert space H, and to every Poisson algebra, a space of observables B of H, And we've also got that the space of observables has a Lie bracket. There's a Lie bracket for conjugate observables in quantum mechanics, and that should be A commutator B is minus I h bar. And you can talk about conjugate observables on the classical side as well. So you want that this magical quantization map associates in a natural way an H which depends on M and omega, a B of H where each observable A is associated in some way to a function on your original phase space, and for conjugate, and such that when you have conjugate observables, they get mapped to observables on the quantum side which obey the standard commutation relations like that. So that would be great, right? You have some canonical map. You know, maybe mathematics delivers that to you. Maybe there's no physics we have to worry about here. We can just outsource this problem to mathematicians, and they will come back and say, oh yeah, there's a natural map in the language of category theory, blah, 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 which you can always get a quantum system from a classical system like this. Well, the answer is it's garbage, right? And we know it's garbage, as I've emphasized in multiple times in previous courses. It's garbage to assume that there's a canonical map. There is no canonical map, and the reason for that is physical rather than mathematical. So these arrows all point in the wrong direction. What is true is that if you take a quantum system given by a Hilbert space, given by a space of observables, given with this obeying canonical commutation relations, and you take its classical limit, which has a defined meaning in quantum mechanics, then you'll have an effective system which is modeled by none other than a symplectic manifold, a Poisson algebra, and a Poisson bracket like this. That direction works, and that direction is called decoherence. So when you subject a quantum system to decoherence, it becomes effectively classical, and the resulting effectively classical system indeed fits into this framework here. But the point about decoherence is that information is lost in going from this right-hand side here to this left-hand side here. You lose coherence, decoherence. Information is being lost under the decoherence process. So this mythical quantization is an attempt to undo this loss of information here. But that's not a well-posed problem. That does not exist when you've thrown out information. There does not exist a unique pre-image under this decoherence map. So it was always doomed from the outset. However, it's been extraordinarily fruitful program to think about quantization. So although physically it's the wrong thing to do, you should always think of the quantum system, take decoherence, then understand the corresponding classical system rather than the other way around. Mathematically, it's proved to be extraordinarily fruitful. There's many quite amazing results where people have attempted to study this. There's a program known as geometric quantization. Actually leads to some very beautiful maths and some very interesting physics. There are some rather general results known about taking Poisson algebras and building not quite quantum theories where you replace this bracket. You take a deformation of this Poisson bracket here and it ends up being almost obeying this kind of quantum relationship here. There's lots and lots of results that have been developed in the mathematical community in the goal of attempting to find some magical map that goes from classical to quantum. But on the physical level, the correct direction is always the other way. So I think, yeah, I don't want to start the next topic today. So I will end today's lecture on this dichotomy between the classical and the quantum world. Thank you very much.